Emily has been researching theories which result in equations for the radius and width of the habitable zones around various types of star. And in order to give Emily an entirely authentic experience, we invited her to make observations of stars and planets in the Exoclock database. And the hot Jupiters are very common there. So in fact, Emily did make some observations of hot Jupiters, and she's applied the theories of width and radius of habitable zones to those three planets that she was looking at observationally, not expecting them to be in habitable zones, but showing how that might be applied in general. Okay, I think that's probably enough. So over to Emily, and let's see what she's been up to.
Thank you, Rodney. And thanks everyone who's stuck around for the afternoon session. I'll just try and share the correct screen. I've got a couple on the go. Let's see if that one's working.
Yep, seeing your first slide there.
Lovely, thank you. Yep, so thanks to Rodney for the introduction. A few spoilers in there, but nothing that will probably be very surprising. I was interested in taking a look at the potential habitability of a very wide range of exoclock targets, and just decided to narrow down on a couple based on what we were able to observe using Pirate. So I'll talk a bit more about that in a moment. But my background, my first degree was in marine biology before I went on to do more study in physics. And then much like Stephen and Heidi earlier today, have just finished my MSc in space and technology. So forgive me if I do veer off into some of what some of you might consider soft science. I'm really into the astrobiology side of things as well. So I'll try not to get too carried away talking about aliens and things like that. So the project that I undertook was looking at how we could apply existing models to some of our new exoplanet targets as we discover them at such a rapid rate. And also, if I just show you actually what the objectives of the study were, looking at how a planet's orbit and transit might potentially impact any habitability that the planet could exhibit. So managed to look at 3 exoplanets, again, attempting to contribute to the Pro-AM collaboration, the Exoclock project, trying to confirm the ephemerides of our existing targets, but also then taking a look at if any of those planets have neighboring terrestrial neighbors that could be lying in the HZ. So basically, also expanding some of the research into not just the exoplanet, but its host star as well, and taking a look at the HZ around those targets. So the traditional habitable zone definition that we have, it might sound a bit critical to say that it's inadequate for star systems that are different from our own solar system, but there are a few thoughts as to why this might be. When we think about the habitable zone or the Goldilocks zone, we tend to think of a space that there's a terrestrial mass, and we can support liquid water on the surface of that mass, if we want to put it really simply. But this definition does only apply to what we've already observed and what we can see and measure in our own solar system. And even within that range of organisms that we consider when we think about life and what we know life to be, there are obviously a lot of extremophiles, and we don't know how exactly how they would cope in different systems. So that's a working definition of a habitable zone. But from this, we can extrapolate the statistical models that we have that calculate the habitable zone around a solar system such as our own, and apply that to other targets in the exoplanet catalogues, and maybe just suggest which systems could harbour terrestrial worlds, and suggest where the inner and outer boundaries of those HZ zones would lie. So that's what this study was aiming to do. But we are largely ignoring all important chemical factors, things like H2O, which is popularly considered to be necessary for life. Some information about the chemical properties of particularly targets in the exoclot catalogue. We don't have a full set of a full sort of chemical profile. It hasn't been characterized yet for some of our targets. So we're sort of just looking at what could be described as physical properties that might affect habitability. So some of the obvious ones are things like the properties of your star, the energy emitted by the star, how close your planet is to the star, but also in terms of the planet's transit, is it eccentric? Is the planet tidally locked? And other things that could impact any organisms that might possibly live on your exoplanet. So much like some of my colleagues that have already spoken today, I used ground-based observations. I used Pirate, based in Tenerife, and followed Kokori's et al.'s photometry processes using HOPS, and managed to get a little bit of data for these 3 targets. Attempted many more targets, but unfortunately the weather was working against me. So I did just include these 3 targets in the study, and managed to get a couple of confirmations and then a couple of failed observations, as you can see. But the planets are very much there and were transiting. It was just one of the issues from observing from the ground, unfortunately. But using some of the data that was pulled from my observations and some of the data available in existing literature, I went on to apply 2 models to try and sort of measure the habitable zone around the stars for these 3 exoplanet targets. So the first model that I used, there are quite a few available, but one of the best ones, in my humble opinion, is Koparapu's 2013 model, which was, I think, slightly improved in 2014. And this code is available online. I haven't included it in the presentation, but you can go and have a look at it yourself if you'd like to. And then from that model, I stripped it down a little bit for a couple of reasons, which I'll mention in a moment, to create this sort of simplified model, which the purpose of that was because we don't have some of those chemical properties that I spoke about earlier. We are making some assumptions about things like the greenhouse effect and other really important atmospheric conditions that we think are conducive for life. And again, we don't have some of that information available. So what we're forced to do for some of the exoplanets, particularly the ones I looked at in this study, we're modeling based on assumptions about things like the albedo and the optical depth from sort of assumed ranges. And again, these were drawn from existing literature. So moving swiftly on to the results of the 2 models, you can kind of see that, hopefully you can see, is a little bit of a small graph, but the results from the simplified model are in blue, and the results from Koparapu's model are in red. The reason for the enormous range in results is, again, just the reasons that I've just mentioned, that I used a range for the albedo and the optical depths of the 3 targets, which were KEL 23AB, TRES 3b, and TOI 2109b, not knowing exactly what the values were. We did have to make some assumptions there and model each of the scenarios, and that's why we've got this wide range of results. But it is heartening to see an overlap. There are more assumptions made in Koparapu's model, and it is heartening to see an overlap there in where the habitable zones are probably exist around the host stars. But they are still really, really large ranges. Now, what's a little bit more accurate from the results of the 2 models is the width of the habitable zone. So while the inner and outer boundaries might still be in question, the width is a little bit more reliable, hopefully, around the host stars. So I'm rushing through this a little bit, but at least there'll be some time for questions if you have any. So it won't be surprising to anyone that these target exoplanets, which we do characterize as hot Jupiters, absolutely are not in that predicted habitable zone. They're far too close to the star. Hot Jupiters have very, very short orbits, and we would never expect them to be habitable. But when looking at the formation theories of hot Jupiters, it's interesting to see that there's nothing that precludes them from having neighbors that could be habitable. So there are three sort of popular theories of formations of hot Jupiters, and none of them sort of interfere with the existence of some of the previous speakers have talked about TTVs, and if there are neighboring planets, it is possible that they can still be habitable, even if the hot Jupiter, whether it formed in situ or migrated inwards, it doesn't necessarily interfere with the habitability of other planets in the HZ around the host star. So other findings, the transit times where they were able to be deduced were very much in line with the existing literature, so that was good. Although the inner and outer boundaries measured from the two models that I ran, they were not particularly accurate, but what was more accurate was the predicted widths of the HZ around each of the host stars. And it gives room for this modeling to be applied to many of our other exoplanets in the catalogue, and as we continue to discover more. The models can definitely be improved. The models that we used were 1D, and by adding in some more accurate climate information, you could improve the models and particularly draw from some 3D models to, again, just improve the accuracy of the inner and outer boundaries. And the purpose of the study really would be to narrow the search for future space-based observations. So if we're looking for, which are obviously very costly in terms of resources. So when we're looking for planets that could be habitable, we're looking in a more sensible area around the host star before we characterize more of the chemical composition of the planet. Some other findings that were quite interesting, the eccentricity of an orbit may not actually exclude a planet from being habitable. So even if a planet was to swing in and out of the habitable zone, providing it's not too wild, this could still be conducive for supporting life. So it very much depends on how long you're out of the habitable zone for, but a lot of the literature agrees that the eccentricity doesn't exclude a planet from being habitable. And even a tidally locked planet can still sustain water. But again, obviously for a very short orbit planet or a hot Jupiter, of course, we wouldn't really expect to see that. So to wrap things up with a couple of suggested future studies, expanding this modeling and applying it to a wider range of stars and unknown exoplanets. And as mentioned, the purpose of this would be to narrow down targets for future space-based observations. And I guess that's all from me. Whizzed through that really quickly. I was a bit more nervous than I expected to be, but if anybody has any questions, please feel free to pop them in the chat. Thank you.
Okay.
Thank you, Emily. That was a good talk. No, time often goes differently when you're giving a talk to when you kind of do the practicing.
I've got a comment. Okay, so you got these formulae which give you the radius and the width of habitable zones. At the moment, the the effectiveness of the habitable zone idea is perhaps limited by not thinking or not considering what the host star might be throwing at you, throwing into the into its ecliptic plane. So, for instance, M-type stars, much smaller than the sun, when they're in adolescence, they throw out a lot of X-rays and gamma rays and nasty stuff like that, which would strip off the atmosphere of any small planet. So one of the future activities might be to take more account of what stars do to their surrounding planetary retinue in terms of radiation and even stellar winds.
And we have a question from Jack. Have you considered habitable exomoons outside of the classical habitable zone, where tidal heating supplies most of their energy? Do you think these sorts of bodies would motivate a search more or less than the narrower Earth-like we're currently looking for?
Yeah, it's not something that I considered in this study, Jack, but I think you're absolutely right. And I would suggest that some of the observations that actually, Rodney, and you touched upon this before, as we find more of these exomoons, I'd definitely be interested to see what the impact. Sorry, I've just lost your question.
Oh, sorry, I'll put it, see if I can put it back. I'm marking them done as they get. So if it was about, have you considered them due to sort of tidal heating? And then what sorts of bodies would motivate a search?
Yeah, in terms of the energy budget, I think there's a couple, and again, it was a very simplified model that was used, but I think if you, just by adding in a few additional factors to consider the full energy budget, you could certainly find some potentially habitable exomoons.
And then Jack's had a follow-up question, which is, do you know how the possible atmosphere of an exoplanet may widen or shrink the habitable zone? And I would imagine a thicker atmosphere might allow further orbits, is what he says.
Yeah, and in fact, some of the studies, that specifically Kopparapu's, but a few of the other studies that I read were very sort of pessimistic when looking at the atmospheric impact, and they do, a lot of them suggest that in fact things like the runaway greenhouse effect for whatever reason could expand the boundaries of the habitable zone, but I think I'd put some of the references for further reading at the end of the slideshow, so if you did want to read more about that, I think the slides are getting shared, aren't they, after the BAE website. So they are very pessimistic boundaries.
And if you want, you could put up a slide again for a minute now so that people can see.
Andy, I've got a question, a comment. Emily showed her immaturity by suggesting a future project there. Now, you know, if you're in a meeting at work, you never suggest something because you'll always get it thrown back at you. So I'm sure Emily would like to run a project for us. Joking, Emily, but yeah. Never suggest a project. Right. No, a subject after my own heart, this, because after all, I think that's where exoplanet research is going. Is there life out there? I mean, that's the one question, isn't it?
So we don't have any more questions at the moment.
I've got an idea for future work.
Yep.
Okay, so the concentration so far is the habitable zone around a particular type of star. Good. What we need is a subset. Habitable zones around hot Jupiters. How far does the exomoon have to be away from its host planet? And what conditions would allow moons around hot Jupiters to have benign environments? There you are.
The project.
I've got a thought on that, which might slightly torpedo it, unfortunately. But the hot Jupiters tend to be very close to their parent star. And
yes,
therefore,
yeah, indeed, yes.
How easy it would be for a hot Jupiter to hold on to many moons, or whether the proximity to the star might strip away the moons.
But it doesn't have to be a hot Jupiter, does it? Because in our own solar system, we're looking at the possibility of life on some of the moons around their own Jupiter.
Yeah, I was saying that specifically because Rodney was asking about hot Jupiters.
Right.
Yeah, I think you're right, Andrew. And I did gloss over this. I think I speed up a bit when I'm nervous. But the one of the things that I chose not to dwell on, because so many people have talked about TTVs today, it's really interesting to see how many hot Jupiters do have these potential TTVs, and if that could indicate that there is a neighboring terrestrial planet that could be in the habitable zone. So yeah, exomoons, but also neighbors is something that I'd be really interested to look into a little bit more.